Okay, so hello everybody. Today our lecture is going to be on how you analyze cycles and permutations and how it can help you solve many problems. So let's just go over the basics first. So what is a permutation? A permutation is, well, let's say you have a positive integer n, then equal to 1. You have the numbers from 1 to n and you rearrange them to get a new sequence a1, a2, an. So these AI satisfy that each of them is in the range 1 to n and they're all pairwise distinct. And this would be a permutation, right? So of course, permutations, you can see it as you have the numbers 1 to n, and it's a rearrangement of them, essentially. Now, the cyclic way of looking at permutations is by building a directed graph on the n numbers. So you assign a vertex to each number, and you draw an edge from I to AI, one directed edge. So obviously, this every single vertex has out degree 1, so it's a functional graph. And because the function involved here, which is the permutation, is actually a bijection, you can prove that every single component of this graph is going to be a cycle itself. And so we can do this for some graph. Let's say we do it for 4, 3, 1, 2, let's say. So we're going to draw these edges. So it's like 1 to 4 to 2 to 3 to 1. Here it's only one cycle, but in general, it is possible to have any kinds of cycles, and we can prove easily that every single component will be a cycle. Now, why are cycles important? Cycles are important because they can help you understand the permutation in a easier way. Like you can look at changes in permutation. For example, let's assume we have something like, okay, I'll explain in this way. So let's say we have some permutation a1 dot an, and 1 second. Okay, and you look at something like AI and AJ for I and J distinct, and you decide to swap these two. So you want to swap their values, and you want to look at how the graph changes. So does anyone have any idea what will happen? So it's something like you have a1, a2, an, and 1 to n, and you have these edges, right? And what you're doing essentially is you're picking 2 points, ai and aj. So here you have I to j. So if I was going to ai and j was going to aj, we want to get rid of these edges and we want to add the new edges, I to aj and j to ai. So in terms of cycles, this looks like you have something like this. Let's say this is I cycle. There are two possible cases that arise. I and j are in the same cycle or they're not. Let's assume they're not in the same cycle. So you have I to x. X, of course, is equal to ai. And then let's say we have j to y, which is, of course, equal to aj. And this is also in some cycle. And what happens now when you swap things is this edge will go away. So I can cross these out. Both of these will go away. I will go to y and j will come to x. So if we look at what happened to these cycles is, let's imagine we start from x and start following the edges. So you will go around, you come all the way back to I. And from I, we would have gone to x, but because that edge is no longer there, we'll jump over to y. So we go to the different component, and then we traverse that fully. And then we come back to j. And of course, from j, we would have gone to y, but now we go back to x. And so these cycles end up merging across these edges that we swapped, or, sorry, removed. So I hope that's clear to everybody. So this actually shows that if ing are in different components or different cycles, then swapping their values, like their indices in the permutation, it will form a new permutation with one less cycle than we had earlier because the cycles of ing merged. Now there's another case, and that is when ing are in the same component. So for example, let's say it's something like I to x. Of course, this is equal to ai, and this is to j, and this is goes to y, and then it comes all the way back to I. Of course, there are some cases here. For example, you could say that, okay, maybe x is equal to j, x is equal to maybe I, but these cases are, they can be resolved easily. So I won't actually discuss that too much in detail, but let's just look at what happens in general. So I goes to x and j goes to y. And now, of course, as usual, we're going to remove these edges. This gets deleted and this gets deleted. And now what happens to x is that x will now sorry, will be pointed to by j. So you draw this edge, and I will point to y. And so now what happens is we observe that essentially it has split into two components. This is one cycle in itself. You follow along x, you reach j, and then you go back to x. And here what's happened is you follow from y, you go all the way to I, and then you come back to y. So as it makes sense that if I and j are in the same component, then swapping them will break that cycle. And if they are not in the same cycle, then swapping them will merge their cycles. So this is a very useful thing to keep in mind in general. So this is a very useful thing to keep in mind. Yeah. So one important thing this lets us know is it allows us to define something that is called the parity of a permutation. I'll briefly describe what I mean by that. So let's say we have a permutation sigma, sigma 1, sigma. Okay, I'll just call it A actually. So let's say we have permutation A, A1, A2, dot, 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 AN. And let's say we count the number of inversions in this. I hope everyone knows what that is. So let's say the number of inversions is I. Then if I is divisible by 2, we say that the permutation is even. Otherwise, we say that the permutation is odd. So it's just depending on the number of inversions mod 2. So we define the parity of a permutation using its number of inversions. And now what we know is that if we have, let's say, okay, so yeah. So let's say we are swapping adjacent elements in a permutation. What happens to the number of inversions? It either increases by 1 or decreases by 1, right? This is well known. And so in particular, each time you do a swap, each time you swap AI and AI plus 1, what happens to I changes by exactly 1 mod 2, which essentially it flips parity, right? So we can even see the evenness as the number of swaps we need to do, adjacent swaps, to get the permutation sorted. That's also another way of seeing it. And now, if we look at our permutation, let's say it's A, and let's define f of A as, say, the number of cycles in A. So when we build the graph I to AI and we analyze the number of cycles it has, let's call that f of A. Then we observe that each time we are swapping two elements, what happens to the number of cycles is that it increases by 1 or decreases by 1. In particular, its parity also changes by the same amount. This means that f of A plus I is an invariant. Does everyone agree? We're not discussing any problem right now, Harshit. I'm just explaining general theory about permutations. So f of A plus I is invariant throughout the entire process. So initially it was this, and finally it becomes n, right? Because the number of inversions is 0 when the array is sorted, but the number of cycles is n, because it's just going to be 1 goes to 1, 2 goes to 2, etc., etc. And so this allows us to obtain this very useful thing, that is the number of inversions is always congruent to n plus f of A modulo 2, which means that you can check the evenness of a permutation by looking at this, the number of cycles plus n. This plus n is important. Okay, so this actually allows us to construct a linear time algorithm for checking whether a permutation, the number of inversions is odd or even. Because we can use this, and now it suffices to just count the number of cycles. But that we can do in linear time anyway using, say, a DFS. Okay, and another thing I want to talk about is composing permutations. What does that mean? So composing permutations is easy. So you should think about permutations as some kind of transformations that act on this set, right? They act on 1 to n, and it rearranges them in a certain way. So you can call that, let's say, some permutation A. And then you could have another permutation B which does this as well. And then what we define A of B as is something like you perform B, because that comes later, that's closest to whatever your input would be, input permutation. So you perform B on the permutation first, and so you'll get some rearrangement, right? And then you perform A on that, and then you get another rearrangement. And what that final output is what it means to compose two permutations. And in particular, you can define squaring here as just composing a permutation with itself. And of course, this extends to any powers. Another useful thing to remember is that every permutation has an inverse. So you can actually extend this to negative exponents as well. And the way the inverse is defined is simply by you look at the graph that you have all cycles, and what you do is you flip the direction of each edge, and that would be the inverse because you just map ai to I instead of I to ai. That would be the inverse permutation. Okay, I think that's enough theory. We can start doing the problems. Okay, so I'll send the problem link in the chat in case people have not read it. We'll be discussing this problem right now. So I'll explain the problem. Okay, so the problem says that there is an array of n elements a1, a2, dot 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 an, and our job is to sort this. We have to sort this. Inverse permutation. Okay, I'll explain inverse permutation again. So the way an inverse permutation works is that you remember the cyclic graph that we had, right? Every component is a cycle. Now what you do in this graph is you just take each edge and you flip it. So for example, let's say we have 4, 3, 1, 2. I think this was the same example I took earlier. And here we have some graph like 1 goes to 4, goes to 2, goes to 3, goes to 1. This was our graph. So if we flip it, then we get this new graph. 4 goes to 1, which goes to 3, which goes to 2, which goes to 4. And now we can write a new permutation like 3, 4. Let me just quickly check. 1 goes to 3, 2 goes to 4, 3 goes to 2, and 4 goes to 1. So this would be the inverse of this permutation. So that's how the inverse is defined. Okay. Let me quickly get rid of this. Okay. Anyway, so we have an array a1, a2, dot, dot, an, and our job is to sort this array. We want to sort it. It is given to us as the input. N is, I think, up to 10 to the power 5, or at least of that order. Let me check the exact constraints. Okay, it is up to 5 times 10 to the power 5. That's okay. And what we want to do is uh, sort this array. And the kinds of operations we are allowed essentially is you can pick AI, AJ, AK, right? And you can rearrange them as it states in the problem. You can rearrange it so that AI ends up here, AJ ends up here, and AK ends up here. Does that make sense? So for example, this is position I, this is position J, this is position K. You have the rest of the array. Of course, IJK need not be in this order. I'm just writing it this way so that it's easier to understand. In some sense, you are cycling it, right? Like you are transferring this here, and this comes here. So it's like a cycle of length 3. So we're allowed only these kinds of operations, and we want to essentially eventually sort the array. Okay, so first of all, sorting is just a small part of the problem. What we really want to understand is if we have a permutation, like let's say we start with the identity permutation, and let's say to any, like this is, let's say A, right? So to A, we are allowed to perform that cycle operation, right? We are allowed to select I, J, K, and we're allowed to perform that operation where we send AI, AJ, AK in terms of positions to these. So we're allowed to do this operation, and the question becomes, what are the permutations that we can eventually reach, right? So as it turns out, we can describe this very well, and that helps us solve the problem. So first, let's see how we can describe this. So let's see. So first of all, we should look at cycles. Let's take a look at the cycle structure. So maybe we have something like this. And now this is a very complex operation, right? But what we do understand very well is how to swap two elements, right? And so can anyone tell me how we can quickly get to swapping these? Like how many swaps we need to convert this into this?
Two.
Yes, that is correct. We need two swaps. So what we can do is we can swap AI and AJ, and it becomes something like AJ, AI, AK. And we have AK, AI, AJ, and then we can finally swap these two, and we can get this. So what happens is that we did two swaps, right? We did two swaps, which means that if we start with number of cycles as n, okay, n is a bad variable. Let's just call it f of a as before. So let's say you start with f of a. So f of a, it can either increase by 1, decrease by 1, increase by 1, and then again increase by 1, or increase by 1, or decrease by 1 both times. Sorry. And so you observe that f of a can change by -2, 0, or 2. and all of these are even, which means that f of a's parity is preserved. In other words, as we can say, because if f of a's parity is preserved, then so is n plus f of a's. And so what is being preserved is the parity of a, right? A simpler way of saying this is that every swap we change it by exactly one, and if we're doing two swaps, then we just bring it back to how it was. And so the parity of a is preserved under this operation, right? Okay, so because the parity of A is preserved under this operation, it means that if we are starting with this permutation, we can only ever hope to reach even permutations, right? Because this original permutation is even. The identity permutation is even because the number of cycles is n, or you can even say the number of inversions is zero. So that's another easier way of seeing it. So yeah, so the number of permutations is even. Sorry, not the number of permutations, the number of inversions is even, and so the permutation is even. Which means that at all points of time, whatever permutation that we can hope to achieve of the elements, it will have to be even. And this is very useful now because, okay, so we know one side, we know that we can only ever reach even permutations. Is it true that we can always reach all even permutations? Right? Because that's also an interesting thing to prove. Because we do need to know if it is possible to reach all of these permutations. So, for example, let's say we're starting with, let's say we want to reach rather a1, a2, dot, 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 an. And we're starting with 1, 2, 3, dot, 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 dot. So we want to eventually convert this into this by using only the cycle operation. So on this, we can perform the cycle operation. This is what we're acting on essentially. Or actually, wait, I think it is the other way around. We want to sort this array a1, a2, dot, 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 an into this, into 1, 2. So what could be a simple strategy to do it? Okay, well, a simple strategy is to simply, let's say we look at 1 and we figure out the I such that AI is equal to 1, right? So we can just force AI to come to 1 by using the operation as long as n is big enough, right? Because we have enough space to work out where the other elements go. So for example, we can select I as equal to this I, so that's fine. We can select j equal to 1 and we can select k arbitrarily. And what this will do is that it will send I to j, which means that AI's value gets sent to 1, which means that here we'll find A1 and, sorry, yeah, here we'll find A1 and, okay, sorry, I was speaking in inverse again. Here we'll find 1 and A1 will get sent to some other place where the AK was, and then the AK returns to I's position. So we actually don't care about this part yet, right? And we just, like, we've managed to make these two equal. And so we can keep repeating this while there are elements, and in the end we'll have only two left, right? We'll have only two elements left. And that's the problem with two, right? When you have only two elements, you can't even do the operation, which means that if this is successful, then the two permutations must already be equal. And this is indeed the case because when we have only two elements, so it's, let's say 1, 2, so there are two possibilities. It's either 1, 2 or 2, 1, right? But only this is even. So it must be this, which means that it must match with whatever we were trying to match with. Because we know that our operation always preserves the parity. And because we were preserving parity at each point of time, and we already matched the first n minus 2, the last two must automatically be equal because the parity condition is being held true at all times. Otherwise, you couldn't have done it anyway, right? So this gives us an if and only if criterion for all the permutations that we can reach, right? So we can just figure out, given a permutation, if we can ever reach it. And now we can actually think about the sorting. So for example, there are essentially two cases. So let's say we have a1, a2, dot, 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 an, right? And let's say the sorted array looks like b1, b2, dot, 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 bn, right? We can even see this as a sigma 1, a sigma 2 for some permutation n. So we have to find a even permutation sigma so that a sigma 1, a sigma 2, dot, dot, a sigma n is, what can you say? It is sorted. And this is, of course, this is pretty easy. Like you can just literally sort it and you can figure out where each element went. But the problem is here we need to break into two cases, depending on whether all elements are distinct or all elements are not distinct. So let's consider the simpler case first. Let's look at all elements are distinct. In this case, this sorting permutation is unique. That's what makes this case easier, right? So sigma is unique, and we can figure out sigma like just using the normal sort. And once you've figured out sigma using the above algorithm, we can do anything. We can even check the number of inversions of sigma, and we can figure out if that is even or odd to get the parity. Or we can even do an O of n algorithm by just checking n plus the number of cycles. So either case, we can distinguish between sigma being even or odd. And if it's even, then we can sort it. Otherwise, we can't, because we are forced to only sort it this way. The other case is that some, like all elements are not distinct. So there are some two which are equal, right? So there is some AI and there is some AJ which are equal, right? So, okay, so what this tells us is that, okay, there is some a sigma 1, a sigma 2, obviously, such that it is sorted, right? And maybe it is the case that a sigma I and a sigma I plus 1 are equal, because there are some two equal elements. And of course, when you sort them, they will end up adjacent to each other, right? So when this happens, what you can do is, if sigma is even, then we can do it anyway, and we're fine, we're very happy. Otherwise, what happens is, because sigma is odd, what we can do is we can reach this, but this swapped. So we can just swap our sigma, we can change these two, and we can argue that because these two values are equal, even if I reach this permutation, the actual sequence is still sorted, even though that's not what my initial sort told me. But that does not matter, because the values are still the same and it is still sorted. And so in this case, we'll find that, in fact, in this case, regardless of whatever happens, if some two are equal, then we can always do it, right? Because if our sigma is even, then we're done anyway. Otherwise, if it's odd, we can swap two just equal elements, and we'll still have a new permutation which we can reach, because the parity of the number of cycles changes by exactly one each time you swap two, right? So now we can even now we can understand the algorithm once again. So if all elements are distinct, then you figure out what the unique permutation you need to sort the array, and you check if it's even or odd using a linear algorithm, or you can even do n log n and count number of inversions. Or you can go for two, and that is, if some two elements are equal, then you know that regardless of what happens, you will always be able to sort it. So you, in fact, you're just done already. You know that you will be able to sort it. And that is just the discussion for that problem. So does anyone have any doubts? Actually, here, because it's 5 times 10 to the power 5, I think sorting might be too slow, which means that we do need to do a linear algorithm for checking the parity of the permutation. Yeah. Any questions? Okay. Okay. We can go on to the next problem. Okay, I'll send the next. Okay, so I've sent the next problem. Inversion counting. I hope everyone has a problem. Some of you have probably read it before, so okay. So the problem basically says that we have some array a1, e2, dot, dot, n is up to 1500, and now m queries arrive, right? And every query says, I give you some LR, and you have to reverse L to R. You have to reverse that subsegment. And what we need to maintain is the parity of the permutation, right? Because we have to count whether the inversions is even or odd, and we know that's just the same as maintaining parity. So how can we look at this? So this is actually already very easy using all that we know. We know that when we have some permutation, and when we when we swap two elements, some AI and some AJ, note that these don't even have to be adjacent anymore, because the argument works regardless. For the permutation case, we used adjacent because we know that that guarantees the sort. But in general, of course, the swap works for any two indices, of course, distinct. And when you swap AI and AJ, we know that the number of cycles changes parity by 1, because it either increases by 1 or decreases by 1, depending on whether they're in the same cycle or not. And because the parity of the number of cycles changes by 1, so does the number of inversions, which means that each swap changes the number of inversions by exactly 1, which means that the actual values don't even matter anymore, right? I only need it initially. I only need the initial values to compute the initial number of inversions, and I can figure out whether that's odd or even. And after that, I need not even look at the values themselves, right? I only need to focus on the sorting. I think it's useful to observe that the elements in the array are distinct. That is what makes this conversion easy, right? So because the actual swap does not affect, sorry, the values do not affect how the swap affects the number of inversions, their parity, we can just like ignore that and we can just think about it as, okay, so I want to swap L to R, which means that I started with something like AL plus 1 dot AR, and I went to AR minus 1 dot AL. So how many swaps do I need to go from this to this? Can anyone answer?
Scaling of the range length by 2.
Okay, so we can think about this as swapping AL and AR, and we can think about swapping these two and so on, right? So there are two cases to consider. One is that the total length is even. So in that case, it's something like AL plus 1 dot A something, AR. And these are equal sized, right? Both of them have size R minus L plus 1 by 2. And in this case, we need exactly R minus L plus 1 by 2 swaps, because we can just look at this as something like a center, and we can swap the reflections over this line in some sense, right? That's all we're doing. We're swapping AL with AR, like symmetrically just swap all of them. And so it takes R minus L plus 1 by 2 swaps to go from this to this. The other case is that it's odd. When it's odd, then we know that that middle element, which is like AL plus R by 2, it will stay fixed. It will not change, right? Because it was AL plus R by 2, it will remain AL plus R by 2. And whatever happens to the left and to the right, it will just swap, right? And here, how many of these elements do we have? R minus L by 2, right? So here we need to do R minus L by 2 swaps. And so as someone said, the number of swaps is ceiling of R minus L by 2. And so using the parity of this, we can figure out how the parity of the number of inversions changes. And note that we never care what the values are anymore, because we know how swaps change things. So the actual values become irrelevant. All that matters is now the number of swaps, and that is given by this. So because as LR arrive, we can just easily figure out how much it changes by, and we can answer the queries. One important thing to note here is that n less than or equal to 1500 is not even useful for us. We can compute the number of inversions much faster than that initially, right? We can compute it for something like n up to even 5 times 10 to the power 5 if we only care about the parity. Here, I think 1500 was given because now you can even naively calculate the number of inversions by simply checking all pairs. Okay, I think, yeah. Does anyone have any doubts in that problem? So as you can see, this is a pretty tricky problem, but it becomes easy once you think about the permutation and how its parity changes. Like the solution just becomes very easy.
Means the inversion parity. So,
Sorry.
that parity means the inversion parity, if it is even or
I think I'm not able to understand you. Can you type your question in the chat? Okay. The next problem we'll be discussing is square root of permutation. I'll just send the link for that. Yes, parity I had defined earlier. Parity can be defined in, yes, it is, I defined it in the lecture as the parity of the number of inversions, but you can define it as n plus parity of number of cycles. These are all equivalent definitions, and we discussed the proof of that as well. So I hope that's clear. Yeah. Yeah. Okay, so I'll briefly explain what the next problem is. So next problem says that I have some permutation a1, a2, n is up to, I believe, 10 to the power, okay, 10 to the power 6, all right. And I need to figure out if there is a permutation b1, b2, bn, such that b square is a, where of course b square is just b composed with b. You can even think about it as bbi, something like this. Bbi has to be equal to ai. Then no, one swap does not change the number of inversions exactly by one. This is false. it changes the parity of the number of inversions exactly by 1. Yeah, the parity. So even goes to odd and odd goes to even. So in this problem, we can see that squaring is very easy, right? If we are given a permutation, it is very easy to square it. We can just apply the operation twice. But it is difficult to retrieve a square root, right? That's what the problem is all about. So instead of focusing on how we can find the square root, let's first analyze what squaring does, right? Okay. So imagine we have something like a1. Okay, one second. Right. So imagine we have a permutation a1, a2, a3, dot, 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 an. Okay, I'll probably call it b1 because b is the guy we're squaring. Okay. So b1, b2, dot, 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 bn. And we want to square this permutation. So we can look at cycles. So let's just focus on cycles for now. So imagine we have some cycle like u1 goes to u2, goes to u3, goes to uk, goes to u1, right? Okay, we can even look at, say, like a triangle for now. So what happens to the triangle when I square? So when I square, how does the graph change? What I'm really doing is I look at this vertex and I travel two edges and I make that my new stop point. So here my stop point is from u1 to u2, but instead what I do is I repeat that process twice, and the new endpoint that I end up at, that becomes my new destination in some sense. So here, for example, u1 would go to u3, u3 would go to u2, and u2 would go to u1. Which means that if you have a cycle of length 3, it actually preserves itself. Like it remains a cycle of length 3. The elements just rearrange themselves in some order, right? Okay, cool. Now let's look at, say, a cycle of length 4. What happens in this case? So here u1 will map to u3 and u3 will map to u1. u2 will map to u4 and u4 will map to u2. So here we see that in some sense it actually split into two cycles. The C4 became two C2s, right? Okay. Now let's take a look at a C5, maybe. So what happens here? Can anyone give an answer? What happens to the C5? Reverse the edges. Okay, but if you observe, u1 will actually go to u3. So it is not reversing the edges, right? There C3 was pretty small, which is why it reversed edges. Yes, that is correct. It would remain a C5. u1 would go to u3, u3 would go to u5, and it would have this weird star formation. Yeah, something like this. So it would still remain a C5. So C5 remains a C5. And what happens to a C6 now? Can anyone guess? Two C3s. Yes, this is correct. So in general, what is going on? In general, it depends on the length of the cycle. If we have an odd cycle, it stays preserved. And if we have an even cycle, it splits into two CNs. Let's take a look at why this is happening. So when we have something like 2m plus 1, then we can look at our graph. It has, sorry, our cycle, and it has 2m plus 1 vertices. So you can actually think about this as, you can mark these as 0, 1, 2, dot, 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 all the way till 2m. And now what you're doing is you can see this as the set of residues modulo 2m plus 1. And what you're doing to a residue each time are, whenever you square, you jump by 2. You essentially do plus 2. And because 2 and 2m plus 1 are co-prime, this is going to hit all the residues eventually, right? And so it's just going to be another permutation of this very cycle. But what happens in the case of even is different because they are not co-prime. I'll just quickly draw that. So here, let's say this is 2m minus 1 and this is 0. Here what happens is that it gets split into two components. One is the even numbers, because 0 will go to 2 and so on all the way till 2m minus 2, and then it will jump back to 0. So it gets split into this and the odd guys. So it splits into two of these. And so a C2n becomes a 2CNs, whereas an odd cycle remains the odd cycle. Does that make sense? Okay. Okay. So now we have a lot of intuition on what's really going on whenever we're splitting. So we know this, that C2n plus 1 stays C2n plus 1, whereas a cycle of length 2n splits into 2 CNs. So I'll just express this as Cn comma Cn, let's say. Okay. Now let's take a look at our permutation. So it has a bunch of cycles, right? So for example, let's say this is what the cyclic structure looks like. So how can we go about finding a square root? Okay, so imagine that our permutation had all odd cycles. So let's say that all of the cycles had odd length. So I guess that's, yeah, I think that is an odd cycle length. Okay, yeah. Okay, and let's say a couple of triangles or something, and maybe a self loop. That's also an odd cycle. So you have some vertex and it just self loops itself. So maybe you have a bunch of these, right? A bunch of odd cycles. So can we figure out a square root to this? Is that easy? Yes, if it's an odd cycle, we already know that there is some permutation which works, right? So what we can do to figure out how to map it is we first work with a C2m plus 1 and we figure out its image under squaring, right? It remains the C2m plus 1, right? And because it remains the C2m plus 1, you can treat this as a permutation itself on the vertices of the cycle to get the new order of the cycle. And what you can do is you can use this order and you can reverse that order. You can take the inverse of this order and you can apply it on the cycle that's given to you, the odd cycle given to you, and you can retrace what the original cycle looked like, which you would have to square to get this, right? And so it is possible to retrieve whatever cycle you're looking at. And so if you have something like a C2n plus 1, you can figure out another C2n plus 1 which squares to this. And so if our graph only has odd cycles, then it's very easy for us, because for each odd cycle, we can find a corresponding pre-image or a square root. And because of course the cycles never interact with each other when we square, that's also very easy to prove. I'll leave that to you guys. And yeah, because that is preserved, you know that when you square, you're going to end up with the permutation you want. And that is very easy. And I can see, yes, square root is not unique. That is correct. That's a very good observation. Square root is not unique. This you can see by simply looking at the identity permutation, right? So for example, any involution, an involution is something where every cycle has length 1 or 2. So basically it satisfies f of x equal to x. So if you look at functions that satisfy this, these are obviously only, like, this is an involution and it's obviously going to be a permutation. That's also pretty easy to prove. And in this, the cycle structure always is like two things paired up or something pointing to itself. And there are many such involutions, right? There are many of them. And all of them square to the same permutation identity. So it's certainly not the case that square root is unique, right? Okay. Now let's take a look. So yeah, I think someone has already mentioned some kind of a solution for the other case. Okay, but let's discuss again. So the other case is that there is no odds. Sorry, the other case is that you have odd cycles, but you also have even cycles, right? So let's say we have some odd cycles. So let's say we have odd cycles of lengths, let's say n1, n2, nx. So these are the odd cycle lengths, not like the cycles themselves. And then you have some even cycle lengths. Even cycle lengths. So one thing to observe is that when we start with a cycle of length n, we either go into a cycle of length n or a cycle of length n by 2. Like this is true. If some element was in a cycle of length n at some point, then after squaring, it's either still in a cycle of length n, or it's in a cycle of length n by 2, right? Everyone agrees? Okay. So yeah. So now, how can we deal with the even numbers, basically? How can we deal with these even cycle lengths? So for example, look at this even cycle length 2m1. So this cycle that you see, did it happen as a result of n by 2, or did it happen as a result of n? Like what really happened? There are two cases, right? Let's consider both cases. So case one is it happened due to a halving, which means that you started with a cycle of length 4m plus 1 and you went into 2m1 comma 2m1, right? This is one possibility. The other possibility is that you started with 2m1 and you went to 2m1. But wait, that can't happen, right? Because this is even. So it must have split into m1 comma m1, which means that this could not have happened, which means this case is impossible. And that means this case must have happened, which means that there should be actually one more cycle of length 2m1, right? Otherwise, it can't be true. The problem can't be true, which means that because I have this 2m1, I can find some other cycle which also is 2m1. And now I can take two of these and I can find a pre-image of length 4m1. Does that make sense? I'll explain how you do that shortly. But does this idea make sense? Why they should come in pairs? Why even things will come in pairs? Note that this argument will not work for odd, because odd could have come from case 1, that is certainly possible. 2n1 could have decomposed into n1 comma n1, and that could have given you one of those n1s. But case 2 is also possible. It's also possible it was an n1 that just remained an n1. But here it's not possible for the even cycle length to remain the even cycle length. And so this means that the even cycle lengths must appear in pairs. And because they appear in pairs, you can pair them up. And so now the problem just reduces if I am given two cycles of the same event length, C2m and C2m, can I figure out a cycle of length C4m such that squaring them decomposes into these two? So let's say this is A1 maps to A2, AM minus 1 maps to AM maps to A1. Sorry, this should be 2, 2, my bad. And let's say you have B1 maps to B2, B2m minus 1, B2m, and maps to B1. Let's say your cycles look like this. So can we figure out a way to get a cycle of length 4m? Yeah, interleaving them. Exactly. That is correct. We just interleave them by doing something like A1 goes to B1, goes to A2, goes to B2. And what happens now is that because you're alternating them, you interleaved them, so to say, A1 will go to A2 when you jump twice, which is exactly what you want, which will go to A3 and so on. And then B1s will separate themselves. So when you square, it's like these interleaving things, the opposite of that happens. You break it into half according to that split. And so you will get these, which is precisely what we wanted. And so we see that this is like an if and only if condition, and because everything is reversible as well, we've in fact figured out a characterization for when a permutation has a square root. And that is precisely when the even cycle length, for every even length, the number of cycles of that length has to be even. Because like these two M1s you should be able to pair up. Of course, it's possible you had three 2m1s, right? It's possible. And you would have paired these two. But this guy also needs someone else because these two are extinguished, which means there should be one more. And if you repeat this argument, you see that there should be an even number of 2m1 length cycles. So for every even length, you should have an even number of cycles of that kind. There's also like, this is not required in the problem, but an interesting problem that you guys can think about is counting the number of square roots. So how many square roots can you have? That's a very interesting problem to think of. Okay. Uh, I think that should be good enough for today's class. I'm not sure. We yeah, I think we've done a good number of problems. I'll take any doubts though. Any things people did not understand, I can explain them now. So we'll be having another class on this with harder problems. So today was in some sense like a prerequisite class you need to be able to work with. In the first problem with the elements not missing. Sure, I'll explain that. So just a reminder for what we are discussing. So we have some sequence A1, A2, AN. We want to sort it using the three cycle operation, which is like you take AI, AJ, AK, and you cycle them in this way. So you have AI, AJ, AK. You basically rearrange them like this, and you want to sort the array using this. So we know that we can, like we already discussed, that we can reach any even permutation. So if this is even, so remember, this is a permutation on end to end. This does not have anything like sorting associated with it. Sorting comes much later. So we know that using these triangular or three cycle operations, we can go from A1, A2 dot dot AN to A sigma 1, A sigma 2 dot 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 A sigma n if sigma is even. Agreed? Okay. So now what happens is, let's say we sort it, right? So you can do something like you can sort these pairs, right? And when you sort them, you'll get some order of these guys. And so let's say you call that permutation sigma. So you have some permutation sigma dot 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 this. And you know that if sigma were even, then because you can sort it like this, and we already know that is the correct sorting order of the sequence, we would be done, right? Then sigma is even. But the good thing is that if it does not work, if suppose the sigma is not even, it's odd, then we're in trouble because we can't actually reach sigma. But what saves us is that we can change our sigma and make it even while preserving the sortedness. And we know that the parity of sigma changes exactly by exactly one when you swap. And which two elements can we swap? We can swap the two equal elements because we know everything is not distinct. So there are some two equal elements. So there is something like XX going on here. And I can just swap sigma over here. I can use these two to change the parity of sigma, and I can get some new permutation sigma prime, which is apart from sigma by a transposition or a swap. And this has an even this has an even parity, and this is reachable therefore. And because sigma prime also sorts it, because it is the same as sigma in terms of values. And so I'm done. Does that make sense? Sigma is just the permutation itself. Sigma is just the notation for the permutation itself. Sigma you can even see as a bijection from end to end. Whatever. Yeah. Okay. Any other questions? Are there any resources? I mean, I don't know if there are resources as such. Maybe a, there are probably a couple of blogs, but I'm not sure if they're very detailed. Like I haven't found anything like that, I think. Can you list some more properties of sigma? Okay, some interesting properties that I would like, not properties, but some interesting things I would like you guys to explore is maybe something like, let's say you have some permutation sigma. Can you figure out if it's a perfect cube? When is it a perfect cube? So when can I find another permutation B such that B cube is A essentially? And generalizing, what about if I give you a prime P? Can you figure out when there is a permutation B such that B to the power P is A? So this is something interesting to think about. Yeah. Okay. Any other questions? Okay, then I think, yeah, I think we can end the class here.